Let ABCD be a convex quadrilateral with BC equals 2 and CD equals 6. Suppose the centroids of ABC, BCD, and ACD form the vertices of an equilateral triangle. What is the maximum possible value for the area of ABCD? This is quadrilateral ABCD where we have BC equals 2 and CD equals 6. It is given that the centroids of triangles ABC, BCD, and CDA form an equilateral triangle, as I've shown in dark blue on this diagram. We can learn more about this by using complex numbers. Complex numbers are a common way to learn about such configurations as we go into Olympiad levels of geometry. The centroid of triangle XYZ, where X, Y, and Z are complex numbers, the centroid of the triangle determined by complex numbers X, Y, and Z is equal to X plus Y plus Z over 3. We can apply that 3 times to learn about the locations of the centroids of ABC, BCD, and CDA in this diagram. It is conventional to put point A at complex number little a, point B at complex number, which we denote by little b, C at little c, and D at little d. Let's call the centroids of ABC, BCD, and CDA G1, G2, and G3, respectively. Then we know that G1 is equal to A plus B plus C over 3. G2 equals B plus C plus D over 3. And G3 is equal to A plus C plus D over 3. Since this triangle is equilateral, the magnitudes of their pairwise differences are equal. So the magnitude of G1 minus G2 is equal to the magnitude of G2 minus G3, which is also equal to G3 minus G1. And G1 minus G2 is just A minus D over 3. G2 minus G3 is B minus A over 3. And G3 minus G1 is D minus B over 3. So if you multiply this equality by 3, you get the magnitude of A minus D equals that of B minus A, which is also equal to the magnitude of D minus B. So this just basically says the triangle ABD is equilateral. So the thing about the centroids forming an equilateral triangle was really just a roundabout way of saying the triangle ABD was equilateral. So we can now calculate the area of quadrilateral ABCD by splitting it up into the equilateral triangle and triangle BCD. The area of ABCD is equal to the area of an equilateral triangle with side length S, that's just S squared root 3 over 4, plus the area of triangle BCD. We can find the area of triangle BCD by focusing on this angle BCD here. Let's call it theta. Then the area of triangle BCD is equal to 2 times 6 times 1/2 sine theta, which is just 6 sine theta by the sine area formula. So that's just S squared root 3 over 4 plus the law of sine's area formula gives us 6 sine theta for the area of triangle BCD. We can also find S using theta by the law of cosines. We can use it on triangle BCD, and we can find S squared. So we know that S squared is equal to 2 squared plus 6 squared, 4 plus 36, which is 40, minus 2 times 2 times 6, which is 24 cosine theta. And that's just 40 minus 24 cosine theta. If you multiply that by root 3 over 4, you're going to get 10 root 3. That's 40 times root 3 over 4, minus 6 root 3 cosine theta. And then plus 6 sine theta. So that's the area of quadrilateral ABCD in terms of angle BCD, which we have referred to as theta. Now this 10 root 3 minus 6 root 3 cosine theta plus 6 sine theta, that's an expression for the area of quadrilateral ABCD. We intend to maximize that expression, and we could do so using calculus. We can find the derivatives of cosine theta and sine theta and set it equal to 0. But we could also do so using trig identities, because it's easier for those who don't know calculus. And it's pretty simple to manipulate this into a nice trig identity. Let's try to do that instead. So we want 10 root 3, the maximum value of 10 root 3 plus 6 sine theta minus 6 root 3 cosine theta. And now the 6 sine theta minus 6 root 3 cosine theta, we can just express that as 12 times 1/2 sine theta minus root 3 over 2 cosine theta. And 1/2 and root 3 over 2 are the cosine and sine of 60 degrees respectively. So we can just express this as 12 times cosine 60 sine theta minus sine 60 cosine theta. And this is just 12 times the sine of theta minus 60. So that's all we want. The maximum value of sine is 1. Don't forget to add 10 root 3 at the beginning. The maximum value of sine is 1, and that occurs when theta minus 60 is equal to 90 degrees. So theta is equal to 150 degrees. At that point, theta equals 150 degrees. We have 12 sine theta minus 60. This part is equal to 12 since the maximum value of sine is 1. And the maximum value that our quadrilateral area can take, 10 root 3 plus 12. And looking at the answer choices, the answer is 12 plus 10 root 3. That is answer choice C, and we are done. Thank you for watching this video, and please follow my channel if you would like to see more videos.